Hey everybody, I'm Shelley Vohr, and today I'm going to talk a little bit about the process of API modernization. For a little brief background on me, I work full-time on the Electron project on behalf of GitHub, where I've been for the past about 2.5 years. This work has also allowed me to explore and actively contribute to a pretty wide range of open source projects and committees, including Node, Chromium, and TC39. I'm based in San Francisco, drink a lot of coffee, and do a lot of crossword puzzles. So, what is modernization? Modernization means very little out of context, especially in the software world. It's a fun, fancy buzzword, but I can't really give a whole presentation on how you can apply its principles to your own organization without first establishing some shared context for what I mean when I say it. In service of that goal, let's start with the most basic definition of the term I could find as it applies to software. So as we see here, modernization can be understood as the conversion, rewriting, or porting of a legacy system to a modern language, software library, protocol, or hardware platform. That's an okay start, but it still leaves us with quite a lot of unanswered questions. What does it mean for something to even be modern? There's still a lot of wiggle room in that definition that I just gave. And even some of its different components might not all be understood in the same way, even amongst you, the audience. For example, I highly doubt that we all understand modern language to be the same thing. For example, beyond that, can modernization even be universally understood across contexts? The answer to that question, for better or worse, is that it depends. And I know that's probably not something a lot of you really love to hear. It's kind of like running a non-deterministic software program. It doesn't really inspire a whole lot of confidence. But I'm not really here today to give you 30 minutes worth of maybe. So let's unpack that a little bit further. Modernization is something that takes on different meanings in different contexts. And so, for you to really understand and gain concrete lessons from its discussion, I'm going to ground it in practical examples from something I work on every day, the Electron framework. Modernization, as we'll soon see, can also feel a little bit like this. There's not always an obvious path to take, and whichever one you do take can often lay waste your best laid plans. You may now be wondering, why is modernization even something that we actively want to do in the first place? I haven't exactly opened with the most shiny and positive take on the thing. So in principle, we modernize in order to retain and extend the value of a legacy investment, which is an investment that continues to provide core services to an organization. There's a lot of different reasons that you, as a developer, might want to do this. But for better or worse, it's something that almost all of us will at some point need to do. Now, some of you might be familiar with Electron, but before we really get to the good stuff, I think I'm going to do a brief overview just to make sure that we all have the same base understanding of what it is. Electron is a JavaScript framework that allows you to write desktop applications with web technologies like JavaScript, HTML, and CSS. It can be used on Windows, Mac, and Linux, as well as a variety of other architectures and platforms, like Windows on ARM and even Raspberry Pi. It works by integrating Chromium and Node, in addition to a layer of C++ and Objective-C, which allows it to create fully formed GUIs, as well as take advantage of file system and networking capabilities with Node. Typically, desktop applications for an operating system are written in the native language for each. If we take Windows, Mac, and Linux, that now means that you have 3 teams writing 3 different desktop applications to do functionally the same thing. This can be pretty costly, both in terms of monetary resources, feature and development velocity, and developer hours. With Electron, you only need to write your app once, and then it will work on all applicable platforms. And we can't really understand how modernization affects users without first discussing API versioning. An API is, fundamentally, a contract that you, as a maintainer, establish with the people consuming your API about how it's going to behave. When developers have their APIs consumed, the consumers are implicitly signing their end of a contract, and you, as the maintainer, are implicitly signing your end. You can think of an API a little bit like buying a new car. When you buy that car, you've probably got a set of expectations for how that car is going to behave, and how various controls on the car are going to affect that car's movement. Now let's say you've bought that car and it's pretty, it's shiny, and you get out on the highway and you're going 80, and then suddenly the accelerator and the brake, they switch. Now, I don't know about you, I love a good adventure, but I really like knowing what my gas pedal is going to do 100% of the time. Your users are the same. They don't want to risk their app on something they don't feel like they can trust. So now, back to one of the questions I had on an earlier slide. How do you set these expectations? One of the more common ways to set expectations for an API contract is known as semantic versioning, or SEMVer. In this approach to versioning, a version is specified with 3 numeric components. First, major, then minor, finally, patch. As its name suggests, each one of these components confers semantic meaning and allows a consumer to quickly understand how updating their app to a new version is going to affect their app's potential behavior. Major version bumps are made when you add incompatible or breaking API changes. Minor bumps indicate new but backwards compatible functionality. And then finally, patch updates indicate fixes to existing functionality but nothing new. For our purposes today, I'm going to focus on 3 main buckets. Modernization spurred by updates to platform, modernization related to dependencies, and then finally, modernization related to programming language specification. First off, platform modernization. Operating systems maintain their own unique API surfaces, which don't always adhere to the kind of API contract you might be accustomed to. Platforms can't really adhere to something like SEMVer when they're versioning, so instead, they often choose to make updates to their API surface area based on updates with their operating system versions. As you might imagine, this can create some mismatches with libraries, which often need to work across multiple versions of a single operating system. One example of this is Apple's AppKit framework, which contains all of the objects that a developer needs in order to implement the user interface for a macOS app, like windows, panels, menus, scrollers, text fields, you get the idea. As such, frameworks like Electron, which hook into and depend on this framework, need to monitor and adapt for changes as Apple releases new versions of its operating system. The question we then want to ask ourselves is, what's the optimal way to account for this? Let's look at how Electron handled a recent snafu with just such an issue. If you've used macOS, you'll know that there's a tray bar at the top of the screen. The tray bar can contain individual elements, which are known to Apple as NS status items. Electron exposes a module that enables you to create and control individual instances of these elements through the tray module. From the very first release of macOS until 10.14 Mojave, developers could use instance properties on these NS status items to customize their appearance and behavior. Then, in macOS 10.10, they introduced a new instance property, the button property, which also allows you to customize the appearance and behavior of the items. At the same time, they deprecated the previous instance properties. And then finally, in macOS 10.15 Catalina, these deprecated instance properties finally ceased to work. In Electron, this created some pretty nasty consequences. We had been using the previous instance properties up until then, and only actually realized this issue had happened because the tray issues, when we were testing our Catalina, literally just stopped showing up, which, as you can imagine, was pretty awesome. So, as a result, we had to quickly and efficiently modernize our own code for these new constraints. But there is one catch. The button property no longer allowed developers to manually manage highlighting of NS status items. Highlighting, in this case, is the way that the icon appears when you click on it. Previously, you could set it to always appear highlighted, only appear highlighted when clicked, or never appear highlighted. So how do we handle this change? By necessity, this is a breaking change. What we chose to do is to remove this method from Electron version 7 without replacement, since at the time, it was in an early beta, and so we wouldn't be breaking our API contract by doing so. We then noted that the tray would experience display issues in older versions of Electron, and encouraged users to update where they could. As you consider your own app's platform modernization strategies, there are some things I think that Electron's experience demonstrates here. We don't always make the right choices, and so we want to share both our successes and the things that we think we can do better. We determined these breaking changes in practice because one of the core team was doing some testing on macOS Catalina, but this change was ultimately more reactionary than I think we wanted it to be. It's important to strategize research around upcoming platform changes in advance, so that you don't end up scrambling to minimize end-user changes in the same way that we did. Had we done that, we could have avoided users experiencing any breaking changes in more than one supported version of Electron. Next up is language modernization. Language modernization is that relating to the programming language in which a framework or library is consumed. That's important in the case of Electron, because while Electron is a JavaScript framework, its underlying architecture is actually written in a combination of Objective-C and C++. And so, modernization in Electron is modernization that allows developers to use new additions or changes to JavaScript as they are added to the JavaScript to the JavaScript language through the ECMAScript specification. A variety of these are outlined here. Some you might be more familiar with include promises, async await, optional catch binding, or nullish coalescing. Some of these capabilities get to Electron for free when we update our dependencies, like V8, but we'll save that for later and focus on the more costly updates right now. A notable effort in the Electron codebase this past spring was known as the Promisification Initiative, which took most of our asynchronous APIs and transformed their usage from callback to promise-based. We undertook this initiative for a variety of the reasons I've already outlined. Callbacks have their place, undoubtedly, but developers can write arguably simpler and more elegant code and open the doors to even more functionality when they can write promise-based code. So how did we do this? And then how did we communicate this to our users? We actually chose to do it natively. And I can see some of you look a little bit confused by that. Aren't promises a JavaScript thing? So the answer to that is actually yes, but also no. To do this, we actually used an engine called V8, which Google wrote for Google Chrome. It implements the same specification as JavaScript, but in C++. By writing a wrapper over its promise functionality, we could enable our APIs to cleanly return promises at the C++ and Objective-C level, without needing to paper over them at the JavaScript level with something from Node like util.promisify. So basically, promises, but with surprise multi-threading. This looks a little horrifying, I recognize, but honestly, it was pretty fun and arguably a lot better for consumers. We also created a document to track progress of this migration and conform to our own Semver contract by ensuring that the changes were backwards compatible where possible, which means that they supported both callbacks and promises simultaneously for at least one major version to ensure that developers had enough lead time to make necessary changes. We also logged these backwards compatible functions with deprecation warnings at runtime. So was this a totally smooth process? Also no. At a high level, we accomplished our goal with relatively few hiccups. But that's not to say we didn't hit any snags. In one of our more fun bugs, we actually found that if you called one API in just the right way, a native promise chain would trigger an uncatchable promise rejection that the user would only ever see as a silent failure, because we'd actually introduced a way to write non-type-safe C++. Jeff Goldblum was ashamed of us for that. So what did we learn from that adventure? And what can you take away from it? For starters, deprecating methods well is a non-trivial task that shouldn't be done haphazardly. We should have been more clear up front that all changes wouldn't be taking place in one major version, since we occasionally still get issues saying that a promise-based function didn't work for promises when it hadn't yet been converted. We're looking towards our docs to help us better fill that gap. We do want to continue our transition path pattern, however. Feedback from our users indicated that they felt we provided clear context and information on how to upgrade methods that they were already using in production. Finally, we move to dependency modernization. This is modernization that enables access to more modern capabilities through dependencies and not through code we wrote ourselves. For Electron, 3 key dependencies of this nature are Chromium, V8, and Node. Updating each of these gives users access to new features, but also brings with them potentially breaking changes. And so we need to be very mindful about how we coordinate these upgrades. Upgrading Node, for example, gives us access to new file system and networking capabilities, like, for example, recursive RMDir. Since Node also adheres to Semver, minor bumps in Node also necessitate minor bumps in Electron, and major bumps in Node necessitate major bumps in Electron. By upgrading Node, we ensure that we stay on top of security updates and see performance improvements, thanks to the great work of the benchmarking working group within Node's governance. Chromium is a bit of a different story, in that they don't really adhere to the same API contract we do, and they don't support older versions past a fairly short tail. We're therefore always chasing the tip of Chromium's source tree. Security and performance are our primary forcing functions here, as the most secure Chromium is always going to be the latest Chromium, and the performance of Chromium, and therefore Electron, is also going to be better the more recent a version of Chromium that we're using. We also do get some upgrades and new capabilities for free from Chromium, like, for example, the wake lock API that allows you to control screen sleep on different platforms. These capabilities are still a work in progress and are constantly being scoped out and experimented on through what's known as the Fugu initiative. Finally, V8. I mentioned V8 a bit earlier on as Google's JavaScript engine that implements the ECMAScript specification, but in C++. For Electron's purposes, it's also very important that we try to use the latest compatible version that we can. This enables us to access the latest features of the JavaScript spec, including some that you can see on the slide here, on the left-hand portion. V8 also works extremely hard to be performant, and so as we look to make Electron faster and less costly, it's also in our best interest to track V8 as closely as we can. And now to the lessons. We've managed to consistently be updating against Chromium's tip of tree and the latest stable node. But our newly short feedback loop was not without a few difficult lessons. Sometimes, your dependencies won't all play nicely in the sandbox together. And if you know that's going to be the case, it's best to make your version bundling decisions as far in advance as possible. We didn't really do that well for Electron version 6, and so at one point, we ended up having to scramble a little bit and had to use a slightly less than stable version of Node version 12, because we were releasing slightly before it went stable. This was unfortunate, as it didn't really change too much from the consumer end, but it did mildly change some of their dependency modernization expectations. You, as a developer, probably want to give your users the ability to use whatever you've defined as the latest and the greatest. And your users want to access these spicy latest and greatest. Without communication, however, these two converging desires are like a chemical reaction that, given just the wrong measurement of a single ingredient, can accidentally explode the whole lab. What if you and your users have different understandings of latest and greatest? That's a non-trivial possibility, considering that you need to take into account different platforms, opinions, conventions, and what you yourselves are functionally capable of delivering. The only way to set expectations and ensure that your users are aligned with your efforts is to communicate with them as far in advance and with as high a degree of detail as possible. To that end, optimal communication can be understood to fall into three big buckets: ensuring redundancy, communicating early, and providing context. Your users aren't and shouldn't be responsible for digging into the deep, dark depths of your documentation to figure out what's coming up soon. That burden is on you, the maintainer. Upcoming changes, especially those that break or alter existing functionality, should be as discoverable and as context-rich as you can make them. If there's only a single place that your users can go to determine upcoming changes, that's a single point of failure. They miss that, and they might get blindsided. In my opinion, the opposite of a single point of failure is not necessarily no points of failure. Instead, it's multiple, discrete points of failure. We want to ensure that your users can miss one or even two notices and still be made aware of changes, which can only happen if you saturate the information in as many places as possible. And next, communicating early. Communication is always great on principle, but not all communication benefits users equally. Telling your consumers about a change right as it is about to affect them is, for all intents and purposes, indistinguishable from not telling them at all. To that end, you should look towards informing your users of upcoming changes as soon as plans are clear enough that it's unlikely you'll need to alter or recant them. Your users should also be made aware of when a change is scheduled to take effect, on what versions that change is going to take effect, and what they're going to need to consider in doing work for dealing with your changes. A team of 5 might and probably is going to be incredible, but they're going to have to consider this work in a fundamentally different way than a team of, say, 50 might. And finally, context. When you make changes to your API surface, there's going to be a reason that you're doing so. unless there's a security-related or similar concern requiring discretion. Why not share that context with your users? It'll help them understand your processes more and likely foster better community relations. When providing that context, there's 4 main questions I think are important to ask yourself. Why are you making these changes? How does this benefit your users? How might this hurt them? And then, how can they prepare? Answering these will provide a strong contextual base for smoother updates as your project continues to grow. Unfortunately, communication can help against some limits. You can communicate your list of breaking changes really far in advance, but if every major version has 100 breaking changes, it's going to be difficult to keep up, and the cost of updating your library might become too high for some of your users. To that end, it's important to be intentional about minimizing churn where possible. You don't want to throw your users onto an endless hamster wheel of terror, because as we see here, everyone suffers, and you don't want that. Your consumers don't want that, nobody wants that. And as vital as modernization can be, sometimes the best choice can be either to defer or not to modernize. In considering whether this is the decision best for you and your team, there's several things you're going to want to take into account. Chiefly, as I've said over and over again through this presentation, context is key. The information you have today might guide you towards a slightly different decision than the information you have 6 months from now, or the information you had 6 months ago. Codebases live and breathe, and your decision now doesn't mean you can't take a different path down the road. You want to ensure that this change will have veritable positive impact on your project. Perhaps end users won't see a change, but it'll decrease maintenance burden across big parts of your codebase. The real danger lies in modernization for its own sake. If you can't prove impact to some part of your ecosystem, you should ask yourself, are these developer hours going to be worth it? If it would increase maintenance cost or increase technical debt, that would also likely be a vote against. Electron has learned a lot from both its successes and its failures on all these fronts. These examples I've provided in light of our experiences can hopefully help you to shed light on how to make better choices in your own code bases. But our constraints and considerations are going to be different than yours, and so it follows that your decisions may also be. When you return to your code bases next week, I encourage you to view these as heuristics rather than rules. Heuristics require situational interpretation, but rules hold fast across contexts. You also have primary responsibility for the success of your users. You should want the barrier to their success in using your library or framework to be as low as possible. Finally, all modernization requires non-trivial work. If this is something that matters to you, it should never be planned as an afterthought. And finally, I want to hear from you. Do you have thoughts on the future of Electron, the boundary between web and desktop, or what it's like to work full-time on open source? I'll be around for the next 2 days and be more than happy to answer any of your questions. Thank you very much.